Hello everyone. So today we are going to present about how we design the FIR filters using the window method. We specifically focus on two types, which is the rectangular and unwindows. Our team consists of me, THANASEELAN and BALAN, and my metric ID is B12 24 10 500, and my teammate is HAARAN and SUKUMARAN, and his metric ID is B12 24 10 722.
A very good day. I will start with the introduction part. The introduction part is about windowing techniques are widely used in digital signal processing to design practical FIR filters, which is known as uh, finite infinite impulse response filters, by converting an ideal infinite impulse response into a finite length response. The ideal filter based on the sine function cannot be implemented directly because it extends infinitely in time. Therefore, window functions are applied to truncate and shape the impulse response. Moreover, in this project, we just focus on the design of low pass and high pass FIR filters using the rectangular and hand window functions. We also use MATLAB for our simulation. In that MATLAB simulation, we are used to analyze the window shape, impulse response, and the frequency response of each filter. By observing these responses, the trade-off between frequency resolution, transition bandwidth, and spectral leakage are clearly demonstrated. Okay, as the next slide, we are moving to the rectangular window. I want to explain first about the rectangular window. The rectangular window is the simplest and most commonly used window function in FIR filter design. It assigns equal weight to all signal samples within the chosen window length and abruptly truncates the signal outside this range. The sharp truncation preserves the original signal components within the window. However, it introduces discontinuous at the boundaries of the impulse response. As the result, high side loop levels appear in the frequency domain, causing spectral leakage and ripples in the filter's passband and stopband. As we can see, there are two sample diagrams that we are shown in our slide. These are the first diagram and the second diagram of the sample rectangular window. Let's we move to the next slide, which is about the frequency characteristic of rectangular window. In the frequency domain, the rectangular window produces a very narrow main loop which provides high frequency resolution and allows closely spaced frequency components to be clearly separated. This narrow main loop is beneficial when a sharp transition between the passband and stopband is required. However, the rectangular window also generates high side loop levels which lead to significant spectral leakage. This leakage causes energy from the main frequency components to spread into adjacent frequency bands, resulting in ripples in both the passband and stopband of the filter response. Consequently, the overall frequency response becomes less smooth, which can degrade filter performance in practical application. Okay, as a next slide, we want to talk about the MATLAB code that we use for our rectangular window. In this assignment, we have been used two filters, which is high pass filter and low pass filter. Firstly, I want to give briefing about the low pass filter, give its result, explain about its result and the MATLAB code. Okay, now we are looking at the MATLAB code for the low pass filter. These are the code that we are used to create our rectangular window low pass filter. Firstly, we can look at the ideal filter. In our code, we first define the sine function to get our ideal shape that which represent the perfect low pass shape. The second one is rectangular window. We create the window using the once comment, which acts like a block that is 51 sample long. After that, we have been multiply the sine function by the window to the truncate by multiply it two together and normalize the result so the filter doesn't change the volume of the signal. So for the normalization, these are the scales that we have used, which is H over sum to the filter, so it doesn't accidentally amplify the signal. Okay, now we are moving to the low pass filter signal result. We can see here we have been shown the diagram, which is rectangular window and impulse response. Also the last one is frequency response. For the first diagram, which is rectangular window, the top plot shows a sequence of ones that truncates the ideal infinite response to infinite length. So the next one is about impulse response. In this impulse response, we can see that the filter's response is symmetric and ensuring the linear phase property. The last one is frequency response, which we can see that the frequencies below 100 Hz are passed while the higher frequencies are attenuated. Overall, we can observe that the sharp transition lead to a high side loops and spectral leakage, making it less precise than smoother windows. Okay, as I mentioned, we have been used two filters in this rectangular window. Firstly, I have been explained about the low pass filter. Now we are moving to the high pass filter. Okay, these are the coding for the high pass filter that we use to create the high pass filter rectangular window. To make a high pass filter, we use spectral inversion, which is basically means flipping the low pass filter upside down. Okay, for the high pass logic, we have been added one to create sample shift to the filter to block low frequencies and pass high ones. For the windowing, the rectangular window is applied to the high pass sine shape to make it faint. For the normalization, we use the absolute sum X to ensure the gain is 1. Okay, now we are moved to the slide which is about the high pass filter result. Okay, now we can see the high pass filter result of the rectangular window, which is the first one is the rectangular window react for the high pass filter, and the second one is high pass filter impulse response, and the last one is frequency response. So firstly, I want to talk about the rectangular window. For the rectangular window, we can see that it shows a uniform amplitude of 1 for all samples within the specified range. For the impulse response, we can see that the response remains symmetric to maintain the linear phase. For the frequency response, we can look that the frequency below 100 Hz are heavily attenuated while those above the cutoff pass through. So from this, we can observe that this method causes high side loops, meaning it is not suitable for the applications needing precise frequency selectivity. Okay, last but not least, I want to talk about the application for rectangular window. We can see there are few applications for the rectangular window, and we have been listed out some applications for the rectangular window, which is firstly we can talk about the FIR filter design, which is used to truncate an ideal infinite impulse response to create a finite impulse response, which short formally we can call as FIR filter. Secondly is about the spectrum analysis, which apply to time domain signals before performing the Fourier transform to analyze frequency components. The next one is radar and sonar signal processing, used in scenarios where computational efficiency is critical and slight spectral leakage can be tolerated. The next one is embedded system, which we can see the ideal for devices with limited computational power due its extreme simplicity and low overhead. The next one is about a control system which used in non-critical monitoring applications where high precision in frequency selectivity is not a primary concern. The last one is about the educational purpose, which commonly used in academic environment to teach the fundamentals of windowing and its effect of signals. That's all from me, thank you.
Now let's look at the much smoother approach, which is the Hann window. This is what we call a raised cosine window. Unlike the rectangular window that just cuts off, the Hann window gradually tapers the signal down to 0 at both ends. We can think of it as like a fade out at the end of a song. This smooth transition is great because it gets rid of those abrupt discontinuities we saw earlier, which significantly reduces the annoying spectral leakage in the frequency domain. Because of the Hann window is smoother, it has a wider main lobe compared to the rectangular one. This means our transition band, which the space where it switches from passing to blocking, is a bit wider and less sharp. But the trade-off is worth it. It massively reduces side lobe levels, which give us a better stop band attenuation and an overall cleaner frequency response. To begin our implementation, we start with the MATLAB code for our low-pass filter using the Hann window. First, we set our parameters, including a sampling frequency of 1000 Hz and the cutoff frequency at 100 Hz, while defining a filter length of 51 samples. The core of this design involves three key steps. The first one is generating the window. So we use the Hann command to create the bell-shaped curve. Unlike the flat edges of the rectangular window, this shape smoothly tapers the signal down to 0 at the edges, which helps to reduce the mathematical shocks at the ends of the filter. Next one, applying the window. So we multiply our ideal sinc function by this Hann curve. This is a crucial step because it suppresses unwanted ripples, also known as side lobes. Last one is normalization. So we normalize the coefficients so they sum to 1. This ensures that our filter maintains a consistent volume and doesn't accidentally amplify the signal. Moving to our result for the low pass filter using the Hann window, we can see a major improvement in the signal quality. First one is the shape, the Hann window shape. The plot shows the window itself. Unlike the box shape of the rectangular one, this one uses a smooth bell-shaped curve that fades to 0 at the edges. Next one is at the middle plot, which is the impulse response. We can see how the smooth tapering affects the filter's response. Because the window fades out gently, it cuts the sinc function much more smoothly, which makes the final filter response cleaner and more stable. For the frequency response, it blocks everything above 100 Hz. But the big difference is how quiet it is the stop band. There are almost no ripples or extra noise compared to the rectangular version. Now we move on to the code for our high-pass filter. This follows the same smooth approach as before, but with the clever mathematical twist. First, spectral inversion. We use the HHP ideal equals to negative HLP ideal command. This basically takes our low-pass filter and flips it upside down. Next, creating the high pass. By adding 1 to the exact center sample, we shift the filter so it now blocks low frequencies and lets the high ones pass through. The third one is untapering. Just like the low pass, we multiply this new shape with the Hann command window. This is really important because it prevents noise leakage from showing up right at the point the filter starts working. The last one is normalization. So we use some ABSH command to scale the filter. Since high-pass filters have both positive and negative numbers, using the absolute sum ensures the signal stay at the right volume without any errors. Looking at our high-pass results, the difference made by the Hann window is very clear. First, the window shape. At the top, we can see the smooth tapering that we always want. It starts at 0, peaks in the middle and fades back to 0. Next one is impulse response. In the middle plot, we can notice that the response is perfectly symmetric. This is great because it keeps the linear phase meaning all parts of our signal stay perfectly timed with each other. Next one is frequency domain. On the bottom, we can look at how the frequency above 100 Hz flow through with no trouble at all. For the final observation, we can see that Hann window makes the response much smoother than the rectangular one. Even though the cutoff isn't quite as sharp or square, we can get a much cleaner signal with less background noise or ripples. It's very stable and reliable filter for high quality work. Now let's talk about the Hann window, where we actually use them for real life. First one is audio and speech processing, where we used in speech recognition and audio filtering because the smooth transitions preserve signal quality and minimize audible artifacts. Second one, spectral analysis, which is ideal for minimizing leakage in power spectrum estimation, especially for the signals with overlapping spectral components. Third, the filter design, where the Hann window preferred in FII design when a balance between smooth transitions and minimal ripple is needed. Next, the vibration analysis, which is the Hann window really effective in reducing the leakage when analyzing closely spaced vibration frequencies in mechanical systems. Next, medical signal processing. Hann window used for analyzed EEG or ECG signals, where reducing high frequency noise and ripples is vital for accurate diagnosis. Last one is general smoothing, applied as a general purpose smoothing tool to reduce sharp discontinuities in finite length data sets. Now that we have seen both filters in action, let's look at the comparison table to really understand the trade-offs. When we talk about the main lobe width, the rectangular window is narrow, while the Hann is wider. In simple words, the rectangular window has a sharper, more focused cutoff, but the Hann window is a little bit fuzzier at the transition point. However, when we look at the side lobe level and spectral leakage, we can know that the rectangular window is high and severe, meaning it creates a lot of noises. On the other end, the Hann window is low and reduced. This means the Hann window is much quieter and cleaner and more stable. So we can say that the rectangular window gives us the high frequency resolution, and the Hann window gives us a smoother and more stable result with less interference. So for the conclusion, we can conclude that both the rectangular and Hann windows are really important tools when we designing the FIR filters. It's not necessarily about one being better than another. It's more about choosing the right tool for the specific job we are doing. If we need a filter that has a very sharp cutoff and we need it to simple as possible to build, the rectangular window is a great choice. But if we are looking for a smoother result where we need to reduce the unwanted signal like noise and leakage in the signal, then the Hann window is definitely the one we have to choose. At the end of the day, picking the right window is the secret to make sure our filter actually performs the way we want to it. That's all from us. We hope this gave you a better idea of how our windowing helped us to build the practical digital filters. It was great showing you our MATLAB results and how the rectangular and Hann windows really changed the signal. Again, thanks a lot for listening to our team's project today.